Video, I will present my final project for CSCIE104 Advanced Deep Learning. The project I chose was Lag-Llama towards foundation models for probabilistic time series forecasting. Time series forecasting is a critical component across various domains where prediction of future values based on historical data supports decision making and strategic planning. Traditional statistical methods including ARIMA, VAR, and exponential smoothing have long dominated the field. These methods, while robust, often require assumptions about data stationarity and linearity and generally lack flexibility in handling complex or nonlinear time dependencies without extensive manual tuning. The use of machine learning algorithms in time series forecasting methods introduce nonlinear predictive capabilities without the assumptions required by traditional statistical methods. In recent times, the integration of deep learning has revolutionized time series forecasting further. Deep learning methods, particularly RNNs and LSTMs, can capture temporal dependencies and have outperformed traditional models in many applications. More recently, the use of transformers has shown promising results, especially in handling long-range dependencies and large data sets, which are typical challenges in time series analysis. In 2023, Rasool et al. Introduced Lag-Llama, which is a foundation model designed for univariate time series forecasting. It utilizes a transformer-based architecture which employs a decoder-only setup using lags as covariates. This design allows it to leverage both recent and past information effectively, which enhances its predictive accuracy. As Lag-Llama has been trained on a large corpus of time series data, it shows robust zero-shot and few-shot generalization capabilities across various domains. This has enabled Lag-Llama to adapt to new unseen data with minimal fine-tuning, which addresses the critical challenges in traditional forecasting methods, generalizability and adaptability. In this project, I will test the utility of Lag-Llama on 10 different time series of economic and retail indicators from Federal Reserve Economic Database. To begin, I do perform zero-shot forecasting on the dataset using only the pre-trained weights. Then I perform model tuning by adding training data. Finally, I perform the hyperparameter tuning to understand the relationship between different hyperparameters and their effect on the model performance. I briefly discuss the setup to set Lag-Llama on Google Colab. First, clone the GitHub repo, then install the requirements using the requirements.txt file, which is available in the repo, and then finally download the pre-trained model using Hugging Face CLI. Analysis, I selected 6 different economic and retail indicators from Fred to understand Lag-Llama's performance. I tried to use both seasonally and non-seasonally registered time series. I did that for 4 indicators to see if Lag-Llama can predict seasonality well. The indicators was chosen to have a mix of linear and non-linear trend data, again to understand and to analyze Lag-Llama's performance across different types of time series. The 10 triggers I used with their descriptions are present in the table here. In this slide, I briefly discuss how to prepare the dataset. First, I import all the necessary libraries. Then I set up the Fred series IDs for the 10 datasets. Then I define the start and end dates, which the start date I chose was January 1, 1970, and the end date I chose was January 1, 2024. For some of the time series, there may be missing values. I explicitly set them up as NA because Lag-Llama can work with missing values as long as they're set to NA. And then finally, I use Pandas data reader to fetch the data from Fred. For preparing the data, I used Lag-Llama for zero-shot forecasting on 10 series. The prediction length was set to 12 so that I get the prediction for the last 12 months. The context length was set 3 times the prediction length. This is what is recommended in Lag-Llama documentation, and the number of samples were set to 2. In this slide and the next, I will discuss the results I obtained from zero-shot forecasting using Lag-Llama. As we can see from the plots, the Lag-Llama model does a decent job in predicting most values within one standard deviation. However, for the bottom 2 figures, which is civilian labor forced participation rate and employment level 16 to 19 years old, respectively, we see that it overestimates the forecast. This overestimate is actually equal to the stochastic shock which was incurred by the pandemic. Interestingly, every other time series I had or selected recovered to its pre-pandemic levels. The only one which did not were these two. So what that means is, without any fine-tuning at the very least, the Lag-Llama model is not capable of handling stochastic shocks. I will continue discussing the zero-shot forecasting results for Lag-Llama. If you look at the top, if you look at the plots on the right here, we can see that the model partially captures seasonal variations in the not adjusted data, but they are not up to scratch. Uh, the unemployment rate values are pretty much like, if you look at the mean, it's able to capture the trend. The seasonality is still up for question, something which we'll investigate down the line. Of all the 10 series, the model performed first on retail sales, both seasonal and non-seasonal. I think for this we would need further investigation, which I would do down the line and discuss the results of, which would involve model hyperparameter training and model fine-tuning. I perform model fine-tuning by adding some of my trained data to get better weights, which are more suited to my data set. To do this, I first extracted the existing estimator arguments, then I initialized the Lag-Llama estimator, and then I initialized the predictor, which would actually take in the training data set to fine-tune the model weights. And then using this predictor and the evaluation functions within Lag-Llama, I generated forecast on my test data. Fine-tuning, the results which I actually got were surprising. Turns out the fine-tuned model performs worse than the general model. I think in my hypothesis here is that all of these time series are disparate. They have their own characteristics, and when we run fine-tuning on all 10 of them together, they don't produce the fine-tuned weights are not suited for the best results, to produce best results for individual time series. It tries to reduce the loss function overall, and to that end, it produces subpar characteristics or values or forecasts for almost all of them. Also, I observed the model weights focus heavily on series with larger units, and they try to fit them in better, which leads to poor performance on models which have lower actual values. So, for example, the model's focus would be to reduce the RMSE of retail sales because they are in millions of dollars versus unemployment rate, which is in percentage. So to test my hypothesis that training on the all 10 series together for fine-tuning produced bad results, and if we narrow our scope, then the results should be better. I ran the fine-tuning on two indicators, but included both seasonal and non-seasonally adjusted data. The reason I did include both seasonal and non-just seasonal instead of focusing on just one was because, in my opinion, one of the biggest powers of Lag-Llama is its generalizability and adaptability, and its ability to perform forecasting simultaneously on multiple time series. So rather than focusing on one data set, I wanted to include two data sets in each fine-tuning, but ensure that they have similar characteristics underneath. So if we look at the results on the plots on the right and focus on the retail sales, both seasonal and non-seasonal, the results are much better than before. In non-seasonal, actually, it captures the seasonal trends much better. We see the peaks and the troughs align. In the seasonally adjusted data, which is the plot or top left plot, we still see some dissonance. The series eventually uh, diverges from the mean. That the forecasts diverge from the actual values. So this one is not that ideal, but the results are much better than they were before. I then ran the process on the home price, Schiller Home Price Index, and again, seasonal and non-seasonal data. And the results here are astonishing because it more or less clearly matches the actual values. So this kind of reaffirms the belief that while fine-tuning, we should actually ensure that the series we are performing fine-tuning on, if we have multiple series, have similar characteristics. Part of the project, I ran hyperparameter tuning to find the best set of hyperparameters for the best model performance. I focused on retail sales for this particular part. Selected the four hyperparameters I selected were epochs, context length, learning rate, and shuffle buffer, and I selected 4 values for each of them, and they can be seen on this slide here. This model took 10 hours to run, and the final results were epoch 10, context length 64, learning rate 10 to the power minus 3, and shuffle buffer length of 2000 produced the lowest MSE. The epoch length and learning rate values were a little surprising, but to analyze it further, I did some analysis on interrelationships between different hyperparameters and MSE, and I'll show them in the next slide. On the right here, I tried to understand the variation in the MSE values when we focus on only one hyperparameter at a time. So we can see that across all hyperparameters, we can consistently achieve a low MSE value. So what that means is, like, if we look at the epochs one, we have a low MSE value for epochs ranging from 10 to 80. So the dependency is not only on there's no one hyperparameter which overpowers the performance. Even if one of them is, so to say, poor, if the other three are your better hyperparameters, the result would be better. So I think to decide on the hyperparameters, we should have variance as a decision factor rather than the actual value. So based on variance, I would say that the learning rate and the number of epochs are critical hyperparameters because they produce the least variance and their mean MSE tends to be the lowest. So focusing on optimizing these can lead to the most significant improvements in model performance. To analyze the interdependencies and relationships between different hyperparameters, I developed 2D heat maps to select the best hyperparameters. As you can see here, a learning rate of 10 to the power minus 4 almost always produces great results irrespective of the values of all the other hyperparameters. Then in epochs, 80 produces the best result generally. For shuffle buffer length, 2000 outperforms all the other values. For context length, 64 is the best, and this was actually present in Lag-Llama in the Lag-Llama paper as well, that the model performance rises up to a certain context length and then starts decreasing. That's the same we see here. I evaluated Lag-Llama model for time series forecasting on 10 economic and retail indicators from Fred. I saw decent performance in zero-shot forecasting with some overestimation in certain series. Fine-tuning, if performed on similar type of data sets, actually improved model performance. For hyperparameter on retail, tuning on retail series or retail sales, we actually saw that the learning rate and epoch value were the most important hyperparameters. Overall, the Lag-Llama is promising and very exciting as it can generalize across different time series and provide decent results. But there is room for improvement in handling stochastic shocks and seasonal variations. Thank you so much, everyone.